Good evening, everyone. You may wonder what an astrophysicist is doing speaking about genetics. And that's because a lot of what you might want to do in genetics involves quite a lot of maths. I'll spare you the maths, you'll be pleased to hear. But I'll talk a little bit about the future of DNA testing. And because Michelle's gone into a lot of the cutting-edge stuff about autosomal DNA testing, and because Y-DNA testing is my field, I'm going to concentrate on the Y-DNA testing side of things here. So why would you take a DNA test? Why are people here taking a DNA test? If you're looking at your genealogy, there's pretty much three things that you want to know. You want to know who your ancestors are, you want to know when they lived, and you want to know where they lived and died. So those are the three things you can put in family trees and try and work out where your ancestors are from. And it's the same thing that we want to do with genetic genealogy. We want to know how we're related to the other people who are testing, or to ancient DNA testers. We want to know when we're related to them, and we want to know where our common ancestors lived. So the purpose of DNA testing, in my view, certainly, is to answer these three questions. And there's different approaches that we can take to doing this. As has been mentioned, genetic mutations are random. So if you want to create, say, a SNP down here, you might change an A to a G in your genome, you might change a C to a G. It's a roll of the dice. If you roll the dice and you get a 6, you get a mutation. And some people get more than others. Now, if you want to see how you're related to people, the more mutations you are different to someone else, the older your relationship. But it isn't a perfect system because these processes are random. Some people might be relatively closely related to you and be more distantly related to you in actuality than people who are genetically slightly closer matches. So there's some element of randomness here. And by testing deeper, by taking more tests, you take this random element out of things. And you can more accurately work out how you're related to other people. We've seen the evidence from the earlier talks about how you go from 37 to 67 to 111 markers and onto big Y testing, how you can narrow down the range of your matches to the people who are actually closely related to you. Now, if you're looking at your 37, 67, 111 marker matches, and this has been alluded to before, normally what happens is if you take two lines descended from the same person, you can expect that you might have a couple of mutations in there. So you can work out the genetic distance between a person and another person. And in this case, one person's got 12, one person's got 14 on this particular STR. And so there's genetic distance of 2, it's caused by 2 mutations. But if you're looking at STRs, then there's a whole slew of other problems that you can have. They can mutate backwards, so you can get zero genetic distance out of 2 mutations. You can have convergent mutations, where 2 lines have the same mutation. And you can have a multi-step mutation, where you end up with 2 extra repeats being allelosely corrected, 3, 4, 5. So you can have situations where the number of mutations doesn't always match up to your distance from another person. So for this reason, STRs can only give you an insight into how closely related to someone, but not an actual accurate result. Nevertheless, they are useful. What we're moving on to now, increasingly as a community, is SNP testing, and this is actually reading the whole genome. In this case, the Y chromosome of the genome, but we're also moving on to whole genome sequencing and actually reading the entire set of genes that you have. Now, we've said, I mentioned earlier that there's 57 million of these A, C, G, and Ts in the Y chromosome. There's something like 1 billion in the whole genome. I can't remember exactly the number. But the major tests that we're looking at now, either the Y Elite from Full Genomes Corporation or the market leader, the big Y700 test, they're testing about 15 million of those. And the really expensive ones that you can buy, the long-read chromium tests, they cost a couple of £1,000. They're testing up to 20 million, but you also get the autosomal DNA in that as well. We can read up to 23 million at the moment out of those 57 million. The rest is just repeating as far as we can tell, garbage DNA that's used there as genetic padding to stop the Y chromosome wasting away to nothing. So if this is the limit of what we can test, and we're not sure whether it is or not yet, then there's going to be relatively little improvement in the future beyond the tests that we already have. We might be able to increase the coverage that we have by an extra 50% or so. So even the big Y test that we have now, we might be able to do 50% better. But there's limited room for improvement here. And that means that we can't always say, okay, well, let's identify a SNP progenitor or someone like that. We can't say, okay, if we've got two descendants of a particular branch, we're not going to necessarily have a SNP that differentiates the two branches. What we can hope for is that the cost of these testing platforms comes down. STR testing is probably about as cheap as it's going to get, but we've seen the cost during sales particularly of these sequencing tests, like the big Y test. These are starting to come down a little bit every year still, and so we're getting slightly cheaper tests, and this is coming because the companies are paying off the initial cost of these big machines that they do to use to do these tests. If we get cheaper tests, that encourages more people to test. We get larger databases quicker. And with larger databases, you get more matches. You get relationships that are much closer to the present. You can tell more about your ancestry. And you can bridge the gap between conventional genealogy and genetic genealogy a lot better. So this is mostly what we can hope for. Mostly larger databases, not necessarily much improvement in the tests. So we've discussed a little bit already, and it's been mentioned about the dating when you're related to someone. Even though this is a random process, there's still a characteristic timescale that's involved in it. If you're having a roll of the dice, you can expect the 6 to come up once every 6 rolls. In the same way, we can expect maybe a mutation to occur once every 6 generations, or thereabouts, depending on the test that we're taking. And this provides a molecular clock. It's not a clock that ticks evenly, it's a clock that ticks randomly. It's irregular. But we can use statistics to convert the number of new mutations that we see in a test to a range of possible ages. And this is not necessarily a very accurate range. We can maybe get it down to a century if we try really, really hard, but most likely we're looking at a few centuries, or for older haplogroups we're looking at maybe recognizing the millennium that occurred. And the reason is that DNA mutates quite slowly. If you look at a particular position on the Y chromosome, then it might experience a SNP once every billion years or so. So that's the reason the big Y tests now test 10 million base pairs to get that 1/4 billion years down to 125 years. And now the updated big Y test, we're getting roughly 1 mutation every 84 years or thereabouts. We can maybe get this down to once every 60 years or maybe once every 50 years in the future, but that's really the limitation of what we can do with SNPs. And you can use this to say, okay, we've got this number of SNPs, we know how many years we can expect to take to form a certain average, and we have a certain number of lineages that share a particular set of SNPs and have a particular set of SNPs that are unique to those particular lineages. So if we've got 8 SNPs that don't match between 2 people, we can multiply that by 84 years and divide by those 2 people to get an ancestor that's about 300 years ago or so. Comparing different types of tests among these tests are difficult. The numbers are very uncertain because of this random process. And there are a lot of nuances in this kind of testing that means the answer that you get out might not necessarily be the right one. These can be accounted for if you look closely at the genetics involved, and you can create automatic mechanisms to do this. But it's, to first order, this is the sort of thing you can do with DNA testing at the moment. It's just a case of automating it. You can do similar calculations for STRs. They've got different problems like the back mutations, convergent mutations I mentioned, but it can be done. And what you can do is you can draw up tables like this, where you say you have a particular genetic distance between people, in this particular set of tests, therefore you're related in this set of ages ago. So you might have 11 mismatches from someone in the big Y700 tests, the STR sample, so you know you're roughly related within the last 300 years or so. And you might do the same with the SNPs in your data. You might have 4 SNPs different from that person, so you know you're related sometime, probably more than 150, but less than 900 years ago. So if you can combine this data, you know you're related probably somewhere 200, 300 years ago most likely. But there's a lot of caveats in here, as I mentioned, so even that's no guarantee. So what we need is to better calibrate these mutation rates. We need to better understand them, to reduce the uncertainty involved in here. We need better mathematical methods to account for these problems, and it's something I've been working on the last few months. And we need to integrate these methods either as third-party tools or directly in the testing companies' websites. And this is something we're trying to get funding to do in the future. So hopefully, in one form or another, these kind of mechanisms are coming to a website near you soonish. So the final problem that I introduced was where. Where are you related to people? And in principle, this is a simple enough problem to look at. You've got, say, someone in Dublin, in Edinburgh, in Paris, and you know that they share a relationship at some point back in the past. Well, where did that common ancestor lie? Well, it's probably somewhere in between the 3 points. And you can use this kind of mechanism to plot a family tree onto a map like this and try and work out where your ancestors came from. So if the ancestors of, if the next most closely related people to A, B and C are D and E, and they come from Copenhagen and Berlin, then you might think that the common ancestor of A, B, C, D and E is born somewhere up there in Flemish country. If you try to do this for real, you end up with completely different ideas depending on the information you put in there. Now the red track here, these are all migratory tracks that have been calculated for a particular haplogroup, that's 4004. I've chosen that one because we've got ancient DNA, we know where it's from. And this is 3 different methods of calculating the migratory pathway between 6500 BC and 1700 BC when this haplogroup formed. We've got a lot of data for this haplogroup, we know where it's from. And if you give the computer free rein on this, you start off in Turkey, you go on the bottom of the Mediterranean, you come up, you take some diversionary path through the North Sea, and end up somewhere in Scandinavia. That's if you give the computer free rein. If you let the computer, if you give them some indication of where you think the starting point is, then you end up going north of the Black Sea, which is the correct path. But then you come up the Danube Valley, and this has actually also been programmed in. And then it all goes haywire again, you end up somewhere in the Netherlands. Now, if you take into all the ancient DNA into account, if you map what we know about the archaeological structures, if you take the S4004 progenitor, we know that there's an ancient DNA result in that line very close to Prague, so we can stick Prague on the map in the level above 4004 here. Then we can actually see that the correct path is something more like the purple one, and this is what we're trying to reproduce. Now, why don't we get this right? Well, the problem is that there's very strong regional biases. If you look at people who do DNA tests, they're mostly Americans or Australians or Kiwis, and they are generally descended from British populations. So we've got a very strong British hours testing bias. Conversely, we have the situation in France, where we have very few genetic testers because the laws there don't necessarily prohibit DNA testing, but it's ambiguous as to whether the kind of DNA testing we're doing here is legal there or not. So we have to take out these biases, and we have to correct for things like the fact that certain families test very deeply in certain locations, whereas they don't sample the wider genome very accurately or very homogeneously, shall we say. And also history is very lopsided. If you look at these migrations that are taking place, we've got, say, one family in Germany It's actually the Queen's ancestry, where it's almost died out in Germany. There's only one person left. And all the diaspora from that family have migrated over to the British Isles at certain different points. They've migrated into Belgium, into Bulgaria, and to all sorts of places, but there's very few left in Germany to actually test. And these thin haplogroups, ones with very few descendants, have got very little data, so we're never going to be able to solve these problems unless we've got these branching structures left alive to exist. And if you have a look at the public testing that we've got, only about a third of people actually state where their ancestor is from in a clear and obvious way that we can use for these machine learning analyses. So what we need is to improve our debiasing of this data, to improve the mathematics that we're using to solve it, and to actually include this ancient DNA results more clearly, and trying to get funding also to do this. Finally, if you are doing your own DNA testing, you can't expect an exact solution unless you've got a paper record to back that up. Your genes don't contain the information about your ancestors' names. They don't contain information about where they're from. They don't contain information about where your ancestral path migrated. You have to piece that together from other documentary evidence, whether it's genealogical records, historical records, paper trails, statistical mapping, ancient DNA, all of these kind of secondary characteristics. In my own line, I go back to Alexander Donald. He was born in Aberdeenshire. We don't know exactly where he was born because his marriage certificate says he was from the parish of Fintray, but he was probably only working there as an agricultural labourer. It was a time of famine, and a lot of people moved around at that time. We don't know where he's from. If you go to council records, we know that the Donald surname in the region existed for about 600 years before that, first records in 1430. But DNA testing Donalds in the area mean that there's lots of different origins for the Donald surnames, at least 4 or 5 within 10 miles of Aberdeen. But what I do know is that I've got a cousin, a genetic cousin, who matches me, who descends from Aberdeen. He's actually there from Aberdeen. And we've got other families with different surnames who trace back to Aberdeen to within a few miles of the city itself. So I know that my ancestral surname is Donald. I know if I'm looking in the records, and there are records I haven't explored yet, that I need to be looking for the surname Donald, because that's been used since probably the 1400s. I know that the family traces back to the city of Aberdeen, or at least within about 3 miles of it. So I know where I'm looking for the ancestral records. I know who I'm looking for, at least in terms of surname. So that really narrows down the search for where I have to go next. So what you, and by you I mean the community, need to do is join DNA projects and help out in actually collecting all this DNA data together so that us researchers can have a look at it and try and develop these products to help everyone. We are encouraging anyone with the big Y data or any other NGS data to actually upload their data to public repositories so that researchers like myself can actually look at it, examine it, and analyse it using these kind of tools. We want everyone to make sure the data is up to date, share as much data as you're comfortable with, make sure that in particular the most distant known ancestor information is accurate in terms of the names that are involved, the places that are involved, the times that are involved, and make sure that there's a latitude and longitude associated with this. And finally, this is meant to be a hobby, some of us take it a little bit more seriously. Keep having fun, keep researching. And I'll say thank you.
Can I ask a quick question? You're talking about the rate of mutation, so once every 6 generations. How do you work that out?
So what we
presumably not from humans.
Oh, we do it from humans actually, yes. Oh. There's several different ways that we can do this, and the main two that we use are current long lineages and ancient DNA. So what we do is we take a pair of individuals who we know descend from, say, a common ancestor in 1700. So we know that there's 600 years of lineages there. We count the SNPs that occurred in those 600 years, and say there's 6 SNPs. If you divide 600 years by 6 SNPs, you end up with 100 years per SNP. And we do this over many tens of thousands of years of genealogies from different people in different places in different countries. And we try and get an average that represents everyone. What we want to check is that this is a long-term average. It's not influenced by geography or history or diet or generation length or anything like this. So we also include ancient DNA studies in here. We say that, okay, this haplogroup must be at least this number of years old because we've got someone who was dug up in 1700 BC who has this particular SNP. So we can say, okay, that's the minimum age of that haplogroup has to be. And we can tie this into archaeological cultures as well, particularly with the Elephant 151 group that represents about 40% of Western Europe today. We know that they have a common ancestor who lived within a few centuries of 2900 BC. So we can actually take all these people's information and do this kind of triangulative process to get back and make sure that it's about that time. So we've got these two different processes with modern DNA and ancient DNA that we can use to try and calibrate this process.
Just very quickly, what's easier, astrophysics or why do you?
Depends on which day you ask me. But the complexities involved in both of them can be quite horrendous.
So we could all do astrophysics as well.
I'm not quite sure if you can handle the mathematics of your team, you can handle astrophysics. I just point at pretty things in the sky and say, ooh.